Hi everyone, welcome to our event. This event is brought to you by DataTalksClub, which is a community of people who love data. We have weekly events, and today is one of such events. If you want to find more about the events we have, there is a link in the description. Click on that link. And actually, when you do this, I don't think it's clickable, but you'll see quite a lot of different events we have in our pipeline. So check it out. Do not forget to subscribe to our YouTube channel. This way you'll get notified about future streams like the one we have today. And last but not least, we have an amazing Slack community where you can hang out with other data enthusiasts. So the link is in the description too. During today's webinar, you can ask any question you want. There is a pinned link in the live chat. Click on that link, ask your questions, and we will be covering these questions at the end after the webinar. Yeah. And now I'm going to stop sharing my screen. And Mikhail, the floor is yours. But while you're preparing to share your screen, I want to tell a short story. So recently, Emily, who is now in live chat, hi Emily, we had a demo of Evidently. You can check this demo in our open source spotlight section. Right now, at the moment of recording this video, this is the last video that we have there. And Emily showed how Evidently works, how you can log all the traces of communicating with the AI agent, and then how you can evaluate it. And then at the end, I was really impressed. She showed how to do prompt optimization with Evidently. So you have some evaluation data set, and you have some evaluation criteria, and you can optimize the prompt in such a way that this optimization criteria is satisfied, let's say. So I was really impressed with this prompt. I started asking you I started asking Emily how this is implemented, and I thought this is a really good idea to invite the person who implemented this to us to give a talk about that. So welcome, Mikhail. It's really a big pleasure to have you here. Not the first time you appear here. Yeah, please, the floor is yours. Yeah, I'm really looking forward to learning from you today.
Yeah, thank you. Okay. Does this work?
It does, yeah. I can see a slide that says prompt optimization.
Yeah, good. 1 second. Okay, yeah. Again, hello everybody. My name is Mike or Mikhail, and today I'll tell you about prompt optimization and our implementation of prompt optimization in Evidently library. First, let me give a quick tour of what we're going to talk about today. First, I'll give you a small introduction about Evidently and the problem we're trying to solve. Then I'll do a review of existing approaches to prompt optimization. Then I'll show you a small live coding example. We'll do basic prompt optimization from scratch. And then I'll deep dive into our implementation and explain how it works. And hopefully we'll have some time for Q&A at the end. Okay, let me start. Most of you probably already know about Evidently. Evidently is an AI evaluation framework. And we started with tabular data, like classic ML stuff, pandas, data frames, data drift, and so on. And now we grew to a complete service with tracing, with dashboards, data sets, panels, and so on. And with the rise of LLMs in the last couple of years, we also added LLM features like text evaluations and LLM as a judge. For those of you who don't know what an LLM judge is, it's basically an attempt to create a classifier, but not using neural networks or statistics or some other complex formulas, but just asking LLM to classify some text for you. In this example, we try to classify the text as awesome or not awesome, but in real life, we can classify for things like toxicity. Does this text have personal information or not? Is it engaging? Is it helpful? And stuff like that. Usually, LLM judges are used to monitor performance of other LLM systems, like your help AI assistant, and you're trying to estimate, is it helpful? Does it do its work? So when we added LLM judges to Evidently, we faced an issue that writing good prompts for LLM judges is hard because it often requires domain expertise. It is time consuming, and small changes that you do to your prompt can have big impact on the performance. So it's hard to know if prompt is optimal or not. But ultimately, it's just a prompt for classifier, right? So we can try to automate it. And we decided to do it with prompt optimization because labeling data is often easier than writing rules into a prompt. And we can learn from those labels and optimize our prompts. So we implemented this in Evidently, but it also can be used standalone without other Evidently stuff. Okay, so when we decided to add this feature, we did a little research. And there are basically 4 groups of approaches that can be used to optimize prompts. First one is search-based approach. It's when you have a pool of prompt variations and you just test each one, evaluate each one, score each one, and then select the best. The example of these algorithms are genetic algorithms, Bayesian optimization, grid search, random search, simulated annealing. The difference between those is how you form this pool of prompts and how you choose which to test next. For example, for random search, obviously you just use random prompt that you generated. For grid search, you just go through all of them. And in genetic algorithms, you usually have a pool of prompts, and then you choose the best performing ones and mutate them somehow to create a new pool of prompts and so on. So the difference is how you create this pool of prompts and how you choose which one to test. The pros of these approaches is that it is systematic exploration, and often you can find good solution with it, but it is slow and it is computationally expensive, and it requires a lot of LLM requests, which means it's not only computationally expensive, but also monetarily expensive. The second group is model internals approaches, which means that you use some internals of the model you're using to guide optimization of the prompt. This may be like gradients, embeddings, token distributions, and stuff like that. Examples are gradient-based prompt optimization, continuous prompt optimization, embedding-based prompt optimization, differentiable prompt tuning, soft prompt optimization, and there are some others. The pros of this approach is that it is very efficient because you're using the same math that LLM using when it inferences stuff. So you're using all the same like numbers and weights, and they can even be differentiated, and this knowledge can like leak into your prompt, right? But the cons of this approach is that it is very limited to differentiable models if you need it, and basically you need to have full access to your model weights and your model inference, and most of us just use LLMs as an API from OpenAI or some other provider. So this is not the case for us. We don't have this access. And also it is very model specific because each model has its own weights, obviously. So if you optimize for one model, it may not be transferable to another model. The next group of approaches is self-improvement. It's basically when we ask LLM to improve the prompt for us. And it is also like using the internals of the model, but not directly, because we don't have access to those. But at the same time, when LLM is optimizing our prompt, it still uses its own weights, right, to generate the answer. So in a way, we also use the model internals. Examples of these approaches are simple one is when you just plainly ask LLM to improve and just use whatever you get back from LLM.
Sorry, I quickly interrupt you. You probably mean, so what I do, maybe correct me if I'm wrong. So a prompt doesn't work. So I just copy it to ChatGPT, copy paste to ChatGPT, say, hey, like for this example, it doesn't work. Can you improve it? And then it improves, and then I copy paste it back and I iterate on this. This is what you mean, right? So this would be simple approach, right?
Yeah, and even simpler, you maybe not copy paste the mistake it made. Just once you're copy pasting your prompt and say, please improve it, and you get something back and you can use it. And
Okay.
usually if the task is not too hard, or if your initial prompt was not very, very bad, then it will work and you can have a little bit of improvement basically for free.
Okay. Thank you.
Yeah, the second approach is APO, which stands for Automatic Prompt Optimization, of course. Also self-refined algorithm, chain of thought optimization, and tree of thoughts. Yeah, as I said, the pros of this approach is that it leverages LLM's own understanding, and it can be creative, like all LLMs are. But with this comes the downside that it may not converge if it's too creative, let's say that. And also quality depends on the LLM, and it also can be expensive because you're making LLM calls not only to evaluate the prompt, but also to generate one. And it can be too model specific. If you optimize for a specific model, it may not work on other models. Okay, and the last group of approaches is example-based. This is when we're optimizing not the full prompt, but only the examples that we add to our prompt, not the instructions themselves. It's also called something like few-shot learning or example selection, demonstration selection, and so on. It is good. It works with few-shot learning, and it really can improve the quality by choosing correct demonstrations, but it doesn't improve the instructions themselves. So there are other approaches, but they're doing their own thing, and we decided that we need all of those approaches combined, maybe without model internals, since our users don't always have access to model weights. So we decided that we need to create our own solution that uses the strengths of all of the approaches. So it's something that works with limited label data, has interpretable results, is practical and easy to use, and integrates well with our APIs for LLM judges. So we based our solution on the third approach, which is self-improvement, but we also used stuff from example-based and search-based. Okay, now to the to the good part. I'll show you a little notebook. I I think we share it, the link for this one.
Yeah, but if you share it with me now, I can share it in on YouTube.
Oh yeah, 1 second. Yeah.
Okay, thank you. I'm going to share it right now. For those who are watching it right now, I will put it in the live chat. For those who are watching it in the recording, you will find it in the description to this event.
Yeah, okay, let me share the stuff too. Basically, it's a little notebook that should look like this. Maybe it will be complete in the link, but you can just delete all the extra stuff and follow along. For this to work, you only need the OpenAI installed and probably the environment variable with OpenAI API key. And we won't use any evidently stuff yet. So here's what we have. Should be 15 examples of some text, like probably tweets, and they're classified into 1 and 0 class. Initially, it is like engaging and neutral classes, but if we use it as text, it makes it too easy for LLM to classify. So we we switched the text labels with the numbers, so it's a bit harder for LLM. Yeah, so let me run it. Yeah, we have two classes.
Can you make it a bit larger? Maybe zoom in like 2 times. Yeah, like that, and remove the panel. Yeah, awesome. Thank you.
Yeah, cool. And I have two helper functions here. One is just running LLM request and return the response. And the second one is to evaluate the prompt. Basically, it runs LLM and then just tries to find the class that it returned it. And if it didn't find any, just returns question marks. So, okay, let's start with writing a prompt. I'll name it bad prompt for some reason. And it will look something like this. Classify this text. Return only 0 or 1 and text. Note that we didn't give any instructions what 0 or 1 means, because it's
It shouldn't work, right?
yeah, surprisingly it will work a bit, because in 0 and 1 there's still some semantic meaning that 0 is something bad and 1 is something good. But we didn't give it any specifics like what 0 or 1 means. And let's write some code to evaluate the examples. So I'll have the array here for results, and I'll loop through them. For example, target in our examples. We'll do the LLM, the evaluate call, and we use our bad prompt and pass the example. And if our result is not the target, we'll print the example and something like target result. And also we'll add the result to our array. We'll add 1 if result equals to target, else 0. And we'll print the results in the end, something like sum of all correct answers, and let's do length of it. Oops. Okay, let's see. So immediately we see that it made some mistakes, and it is like surprisingly well, but usually it's like 10.
I'm really surprised. Like, how did it even know? Because we just said return only 0 and 1, and then it just figured it out. It's really interesting.
Yeah, like 10 is more like this, because like if you do just randomly, then you'll get like 7 or 8. And since there is some uh, semantics in 0 and 1, it actually performs a bit better, but still it's not near the perfect score, right?
I was expecting the random result, to be honest.
Yeah. So magic of LLMs. This is why I need to use zeros and ones, because if we name the classes like bad and good, it will like do 10 out of 10 or 15 out of 15 the first time, and it's not interesting. Okay, so we'll write a meta prompt, which is a prompt to improve our prompt, and I'll do it like this. Is it enough? No, one more. So, and I'll say I use LLM to classify texts. It made some mistakes. Pretty please improve my prompt using those mistakes. And then I'll just give it a tag with prompt. And we'll put, like this bad prompt here. And here are the mistakes. And I'll just copy paste all of this stuff here. And I also, to parse it easily, I'll say return new prompt in new prompt tag. Yeah, something like this. And all we need to do is just run LLM with this and just print whatever we got back. Okay, so we can see that it has like some knowledge already from our examples, but let's just evaluate the new stuff. So I'll copy the new prompt and I'll copy this stuff here, and I'll just switch the bad prompt for the new one. So as we can see, probably, yeah, perfect score. So this is,
Amazing.
yeah, the task here is simple, right? And in real life, you'll get more complex and challenging stuff. But this just to prove that it actually works, and it does. So let me get back to my presentation. If I find it, yeah, here. Yeah, so what we learned from this example, that simple approach actually works. We can just ask LLM to improve, and it does improve. But for this, label data is essential, not only for validation, but for the improvement itself. And sometimes we can get away with one-shot optimization, and we don't need complex algorithms for some, at least some tasks. Okay, so
And
let
before we continue, there is a question. I think it's just right after you presented this. So the question is, so basically when you're not able to specify your requirements, but able to say what is right and what is wrong, you can make LLM deduce the rules, right? And this is what we used here.
yeah, exactly. It's like classic ML versus rules, handwritten rules, right? You don't hard code all the rules. You just show some data, and then some algorithm like random forest or neural network or something like this. It just learns from this data, and this is the same, but like on another level of abstraction from all the algorithms. You just ask LLM to deduce the rules, and it does.
Yeah, and I have a follow-up. Maybe this is something you will cover, but what I observed in the past when I tried something else. So a few minutes ago when I interrupted you saying, hey, how about we just copy a prompt to ChatGPT and give it some bad examples where it doesn't work? I think you implemented something similar. You ask ChatGPT to improve your prompt, and often it helps. But what I also observed, sometimes what ChatGPT does, it says, if the input is this, then make output that, right? So it basically hardcores the examples. So I think the example was, I don't remember, but let's say here, what we did now could be if you see an emoji, or if you see this specific emoji rocket, then output one, right? So then we are kind of overfitting on the emoji rocket.
Yeah, I got you. And I'll say a couple of things on that. It is the most secret technique we used. You'll see.
Okay.
Secret sauce of the prompt optimization. uh, okay, I'll cover it later a bit. Okay, so now I'll tell you about our approach and our interface. Basically, when we use prompt optimization with LLM Judge, first we define the judge itself. For us, it's like defining a criteria, which is a part of bigger LLM Judge prompt. But from the user's perspective, you can just write a criteria using English language, not Python, right? And then you provide some data set with labels. And our automated prompt optimization feature does all of the magic for you. It runs the initial prompt that you provided, which is like the criteria. Then it evaluates it using the data you provided, then optimizes it maybe a couple of times, and then gives you the best result. From the API perspective, it's just one class named Prompt Optimizer, and it is main entry point for this feature. And you provided three things. First is the strategy. It's basically takes all of the logs that we have up until this point, like which prompt we used initially, all of the other prompts, all of the scores, all of the results of other prompts, and it just generates new prompt. All right, so the interface of the strategy is give me all the logs, I'll give you new prompt. And we have two implemented. I'll talk about them a bit later. Second thing is executor. It's something that takes your prompt and turns it into some result, maybe like a data set, or in case of LLM judges, is the classes for the example text. And it can be a function, just a function, so it can be heavily customized, and you can create your own executors basically. And the last thing is scorer. It's how you measure the success of your prompt. It takes results from executors, from single executor, and just return some numbers like maybe accuracy, or of course you can implement your own scorer. And together it works like this. You've got prompt optimizer. I don't have my cursor, okay, but I'll tell you without it. You have the prompt optimizer. It runs some optimization runs, and each optimization run is a big loop where you have initially you have a prompt. You use executor to get results. Then you use results, put them into scorer to get scores, and then you combine all of it, the prompt, the results, and the scores into a thing called run log. And then you try to decide if you need to stop or not. If you're done, then okay, you got the prompt. you can choose the best one if the last one was not the best, of course. And if you're not ready, then you can run the strategy, which takes the run log with all of the stuff and generates new version of the prompt. And then go back to the loop until we're done, and early stops says, yes, we're done. So this is the architecture. The most interesting thing happens in the strategy, and
I was thinking maybe like here it's a bit abstract, but we already have the code that you showed us. And some of the concepts from here, maybe we are able to map to the code that you have.
oh
Right? So
yeah,
for example, prompt is when we ask it to say, hey, output 0 and 1, right? So this is the prompt.
yeah. So okay, let me map it like this. The prompt is the bad prompt variable that we had. The executor is the evaluate function. It takes our prompt and runs it. Maybe not even the evaluate, but the loop that we did to evaluate all of those,
Mm-hmm.
right? And the results are the classes that it returned. We didn't save it explicitly, but they are there. The scorer is the if statement that checks if we got the correct class for each example. So the scores are ones and zeros we put into array, and the run log is all of it. Then early stop is just me. I said that we're not done.
Well, yeah, in our case, we were kind of done after first iteration, right? It was 15 out of 15.
Yeah. But yeah, if we got some mistakes, then we could repeat the process.
In our case, it was simple because it was only 15, but what if we had like 300, right? Then it would require a few iterations.
Yeah. If you got more data, then the higher the chances that something will be off. But as you will see, you can configure early stop to not try to get the perfect score, for example.
And the strategy in our case, you'll probably tell us now, right? What's the strategy?
The strategy is when we created the meta prompt and put the mistakes we collected just inside of it. In the actual evidently code, we do it a little bit smarter, but the idea is the same.
Thank you.
At least for feedback strategy. So now we have two. Simple strategy is what I described when you first asked, what do I mean? It's just asking LLM to improve and nothing else. And the feedback strategy is something that we did in the live coding session. And it's the most interesting one. So I'll talk about it a little bit more. And also it is highly customizable stuff, so you can just create your own strategy and use it if you feel like it. So for the feedback strategy, I guess we already know what it does. First, you execute your prompt on training data, then you identify mistakes where the judge was incorrect. You collect all of those and put it into the meta prompt and ask LLM to optimize your prompt. For each mistake, we not only use the text itself and its target label and its incorrect prediction, we also add human reasoning and LLM reasoning if it's available. And if you use evidently LLM as a judge, there is just a flag to include reasoning into your output. And if you have human experts that label data, you can ask them to write, why did you choose like this class or that class? And it helps a lot because it not only provides the correct answer, but the description why it was chosen, and it helps LLM to extract knowledge from those mistakes. Okay, so here is the actual prompt that we use. in our feedback strategy. Basically, it says, I ran LLM for some inputs to do task, and it made some mistakes. Here's my original prompt, and here's the rows where LLM made mistakes, and then we list all the prompts, all the rows, and please update my prompt to improve LLM quality. And here's the secret sauce that I talked about. Generalize examples to not overfit on them. We
Yeah, that's it.
almost, yeah.
Okay.
Because without it, it actually tried to like basically add all of the examples that we just sent in the prompt that it returned. Yeah, and this helped a lot. Sometimes it still does it, but not so often. Yeah, and then we can add some additional instructions, like users can add different additional stuff to the prompt. Actually, they can even rewrite the whole prompt themselves, but this is like the default value. And in the end, we ask to use tag to parse the response. The mistakes are formatted like this. We just take those 5 fields and format them into XML tags, nothing fancy. Yeah, and the second part of the secret sauce is machine learning 101. If you're trying to prevent overfitting, just split your dataset into train, validation, and test splits. By default, we use 40% train, 40% validation, and 20% test. But this can be configured, of course. The idea is that we optimize on train. So we only send mistakes that it made from train. Then we evaluate the result on validation, and we use the validation scores to choose the best prompt that we got. And we report the final score on the held out test set that has been never seen by the optimizer before. And this prevents us from overfitting and training on examples. So even if some iteration includes the exact examples we provided, it will fail on validation, probably, hopefully. You can never be too sure with LLMs, but yeah. And in the end, you'll got score on your held out test set. And if it's good, you don't actually care if there is a lot of examples and exact examples in your prompt, because if it works, then it works, right? The next thing, I already talked about this a bit, the early stopping. It's a way to decide if we need to optimize further or not. We have 3 configurable parameters. It's max iterations, it's just maximum amount of times that you try to run this loop before giving up. Second is minimal score gain, which means if your score gained less than this amount, then we need to stop. And target score is just to say if we got like 100% accuracy or 90% accuracy, that we can stop and not waste any more compute and LLM tokens on diminishing returns. The last part is also important, and it's multiple stars, because with LLMs, you got a lot of randomness, and sometimes run can stuck in poor local optima because it initially did some bad decision and the prompt is like, let's say, non-recoverable at some point. And if you repeat it a couple of times, then the chances are that some of the runs will stuck, but others will do better. So it's basically, it's not stacking. It's bagging, right? In machine learning terms, I think. So we just
Yeah,
run.
backend is when we do some sort of averaging at the end, but here in our case we take
No,
max,
no.
right? Which is
Yeah.
still kind of bagging, like still ensembling, right?
Yeah. Some kind of ensembling. Yeah. So yeah, and in the end we just select the best one and use it, because you can't average prompts, I think. But I think
I don't think so.
yeah, some genetic algorithms work like this. They're trying to like merge different
Potentially, you can ask an LLM to say, "Hey, I have 3 prompts. Can you please merge them into one?"
yeah, but you still need to evaluate it after, because you will be
Yeah,
not
yeah.
you can be sure that what works in the first and works in the second will work in the third that you get by combining them.
But it's like you have 3 models, linear models, then you combine them, and you still evaluate
Yeah,
the
yeah,
new combined model on the new again on evaluation, right?
yeah,
So it's kind of similar, I guess.
yeah. And also we got performance features. Of course, we execute all the runs in parallel, and we use async and throttling for efficient LLM API calls. So throttling means that we try to use the quota, which is for OpenAI, I think is 500 requests per minute, but we're not going over it. And also we try to cache where it's possible. And we got full audit log, so you can see each iteration and how much time it took, and what was the initial prompt, what was the optimized prompt, what are the scores, and so on. So you can see for yourself and debug if you need it. And just for completeness sake, this is our simple strategy, which is like just asking LLM, and it looks like this. I'm using LLM to do something. Here's my prompt. The prompt, please make it better. Pretty please, LLM overlord. Uh, uh, please make it better so I can have better results. Again, some additional instruction and new prompt tag. It is useful if you don't have any label data, but with the feedback strategy, sometimes you need like 5 or 10 examples, and it already can do magic. Here I have a demo with our code. I'm not sure. Do we have time for this? Because there is
Yeah,
a
if it's short and if it's different from what Emily presented, why not?
uh, I don't know.
Yeah, let's see.
Yeah. Let me. I'll be quick about it. Yeah, let me find it.
Because evidently is also quick, right? You have this parallel execution.
Mm-hmm. Yeah, I think it's this one, right?
No, she presented tweet classification, engaging,
Oh,
not
that's
engaging.
better. That's
Yeah.
better. This is different example.
Yeah.
Yeah, I actually already run it to not waste time on the all the LLM requests, and I'll try to be quick. So basically, we import some evidently stuff, and we read the data set. The data set looks like this. It is some code reviews for actual code, and 2 columns for labeling. One is like just a class, and the second one is reasoning. That is called the expert comment, like why he chose to say that this is bad and this is good.
So the
Yeah,
task of the LLM is to say if the code, like a pull request or something, is good and should be accepted, or it's bad and should not be accepted,
yeah,
something like this.
yeah, and not the code itself, but the review for this code.
Ah, okay.
Yeah, so here we do some magic to, not magic, we just create evidently dataset object, which is the same data frame, but with some metadata, like which column is which, and yeah, and the types of the columns. And here we create an LLM judge. Basically, all we need is this criteria, which is text, and we say review is good if it's actionable and constructive, review is bad if it's non-actionable or overly critical. And then we
Okay,
got,
now I understand. It's like this Linus Torvalds reviews, uh, right? Maybe yeah. Sometimes they are not actionable, but they go viral on Twitter.
yeah, LGTM.
Yeah.
Yeah, so we use this criteria to create a prompt template for this judge. And yeah, we provide this judge here and we set the model and provider. So basically now this will act as a classifier and we immediately just pass it to the prompt optimizer as executor here. And we used feedback strategy and accuracy scorer. And also we set 5 repetitions. So it runs 5 times in parallel. You can see that it's parallel because this is the number of iteration and we have like classical asynchronous printing. Yeah, so if we try to see for the zeros iteration, first it executed the prompt and it is exactly the prompt that we gave it. Review is good when it's actionable, blah, blah, blah. This one. Then we scored and yeah, and we got 50 predictions because we have 50 rows in our data set. Then we scored it and got those scores, which is not very good since like random is 1.5 or 0.5, and it's not really an improvement on the random. And then if we take the next log, we see that it was optimized to something else. Like now it says review is good when it provides clear blah, blah, blah. Then we executed the new version and then we scored and immediately we got like almost perfect score. But on test, it's still not good. But on validation, it is 100%. So I guess this is why we didn't do more iteration in this run. But in some other runs, we got more iterations. Okay, the third run is here. Then we optimized more. And then we optimized more. Okay, so when you run it, you can see the best prompt that it got from all of the versions of all of the prompts. And you can see some stats of this optimization run. So we didn't specify any seed. We've got 50 rows in total. So here we got 20 and 20 and 10 in test. We used 5 runs. The total time was like only 46 seconds. This is how much tokens we used. And this is the best prompt with the score. So we can see that it was perfect on train and validation, but not so good on test, but it's still not very bad, right? And then detailed statistic for each run, how much time it took, each token, each version of a prompt. So we have a lot of this stuff. Yeah, so basically that's it. The only one more cool thing. Sometimes you can even skip the creation of the judge itself that we configured here. And you can use like a blank LLM judge without any prompts or anything, basically. And the prompt optimizer will fill the judge for you using the same algorithm. And we can see that where is it? The best executor. Best executor is the judge that it created. Yeah, and if we see stats, we can see that here we even got better results on the test set. It might be a fluke, and we spent more tokens actually, but maybe our initial prompt in the first example limited the creativeness of LLM. So if we don't provide it with anything and it's free to come up with its own prompt, it can work even better. Okay, so I guess, yeah, that's it for the presentation. This notebook is available
Yeah, I just
in our
shared it.
repo.
I've found it on Google and shared it. I have a quick question about this.
Yeah.
So you have criteria, right, for your judge, and then you have the prompt that you want to optimize. Does the optimizer see the criteria?
Yeah, actually, when you use prompt optimizer with judge as executor, it actually optimizes only the criteria because
Ah,
I'm not sure we can. I can try. Not sure if it will work. So we have the.
so
Uh,
I imagine that the typical situation I have is I have some sort of agent, right? And they have my judge that the judge is saying, let's say, if the response the agent gave is relevant or not relevant, right? According to some specification, right? And what I want to do is I want to change the prompt of my agent, not the prompt of my judge, right?
um, it depends because if you're trying to optimize the judge itself, if you mean the system prompt for the judge or
Yeah, the system prompt.
uh,
The system prompt not for the judge, but for the agent that so we have the agent in production, we have some evaluation set for this agent, and we want to improve the prompt, the system prompt for the
okay.
agent.
Okay. Uh, yeah, but to run this optimization, you need some metric that you can optimize on. And in case of LLM Judge, it's easier because it's like accuracy or something like that. But for your production agent, what is the metric? And if you can answer this question, then you can answer whether you can optimize prompt for it or not. You,
Yeah, typically it's something like if it's relevant, if it's helpful, and then you describe what do you actually mean by helpful, right?
yeah, if you have something like this, then it means your agent is some form of LLM judge, and it can be optimized the same way,
Okay.
right? Okay, let me try to uh, yeah. So this is the full prompt of the LLM judge, and we can see the criteria somewhere. Where is it? Oh, here. Here's the
Okay.
criteria, but the rest of it is like how we provide
Mhm.
the text. We we didn't use text here for some reason. Yeah, and how the response should be structured. So the thing that is optimized is here because this is always the same, and
Mhm.
it's like the wrapper around the actual meaning of the LLM judge.
Okay. We have some questions. Did you finish the presentation? Maybe you have like a
I
couple of
have
slides.
some couple of slides, but it's like yeah. Yeah, so takeaways again, we can use feedback-based optimization and it is effective. It works well even if you have small number of examples. Um, and the simple approach, just ask LLM to improve, actually works. And we have implemented this approach and some additional features. I talked about them a lot already. So the multiple strategies, the overfitting prevention, early stopping, performance optimizations, parallel execution, throttling, blah, blah, blah. And of course, integration with our LLM as a judge feature. And also that it is customizable and you can use it without LLM as a judge too. So if you forgot, evidently it's open source and free, so you can try it for yourself, and you can find the notebook that I just showed you in examples directory. There are also two more notebooks with prompt optimization examples. One is focused on the customization, so you can try it for yourself. Yeah, and that's it. Here's the links to our GitHub, the documentation for prompt optimization, our Discord server, when we can help you with anything, and my LinkedIn profile, because why not?
Thank you, Mike. So I just want to summarize from myself what I learned today. So typically, let's say when I have an agent and I run this agent, and then I have some evaluation criteria for this agent. Typically, these evaluation criteria are, let's say, whether tools were used, like the tools I expect to be used, they are used, or helpful, relevant. I also define what relevant means in this context, and then some problem-specific things like has it included references, right? Things like that. So in all these cases, the evaluations I run, they are binary at the end, right? It's like, has it used the tools I wanted or it did not, right? Like, is the result relevant according to this criteria or it's not, right?
Yeah,
In all
it
these
can
cases,
also be multi-class
yeah,
classification.
okay, yeah. And in all these cases, since I have this binary evaluation, like you showed in the example when we had 0 and 1s, then I can take my prompt that I have. I can also give it the examples that are not working, and then I ask it to optimize, right? And then, but instead of doing that, I can just rely on the library that is already doing all that, has multi-processing, like parallel execution and all that, right? So in this case, evidently, and
Yeah.
I can just use the prompt optimization thing without using the rest of, like, let's say I'm not interested in monitoring. I only want to optimize my prompt. So then I don't need to use the monitoring part, right? I can just take the prompt optimization and
Yeah, yeah,
use it for tuning my prompts. Cool.
yeah. And I also just now remembered how I should have answered your question about optimizing the agent, right? Actually, in our example, we optimized the LLM judge, right?
Mm-hmm.
But LLM judge can also be used as a scorer. So you can pass the function that calls your agent to
Mm-hmm.
generate some response, and
Yeah.
then use judge, for example, like helpfulness LLM
Mm-hmm.
judge as a scorer. So you will
Mm-hmm.
optimize prompt for your agent, and you will use judge score to select the best prompt.
Mm-hmm. Yeah. Great. Do you have 5 or 10 more minutes?
Yeah, yeah, of course.
Okay. Can I please share my screen? I want to share this because we have quite a few questions. Yeah, if it's possible, maybe you can share the slide deck with us. You can do this after we finish, so I'll just put it in the description of the video.
Okay.
Question we have: does it work with very long prompts and very structured prompts? I don't know what does it mean, very structured prompts, but
Yeah, I guess it does work with long prompts if they fit into like context window for the model, because why not? As for structure, I think if it's very complex structure, it might break because like you saw by structure, I mean that in our live coding example, we have the placeholder for text, right? And when we run the optimization, it kept this placeholder, right? So we can use it the same way. But if your structure is a lot more complex, then it might lose some of it and it won't work with your existing code. And this is actually the reason why we optimize um, only criteria for our judges, not the full prompt, because we have basically like criteria and all of the other stuff is just explaining the structure of the response or of the input, right? So we don't need to change that. We only want to optimize the criteria. So uh, in your case, you can try to separate the meaningful part of your prompt from the structural part of your prompt and optimize only the meaningful part.
Mm-hmm. Yeah, because I noticed that sometimes when I use ChatGPT to improve my prompts, sometimes it because I keep all the prompts in Git and everyone should, I can see the diff between the previous version of the prompt and the new version of the prompt, and sometimes it just adds a few lines, which is what I want, or changes a few lines of the prompt, but sometimes it rewrites the whole prompt. And this is not what I want to have, right? And then I guess in my case, what I do is I ask it not to rewrite the prompt, but in some cases it's also okay if just it ditches the whole prompt and creates a new one from scratch, right? So it's not really a problem, especially if you have a long prompt and then the result is shorter, then why not?
Yeah.
Yeah, then there are questions if you compared it to TextGrad and DSPy.
Yeah, we didn't try TextGrad, at least I don't think we
I
did.
don't
But
know what it is. Maybe this is what you mentioned, that there is approach that is model specific, right?
um,
Okay, we can read afterwards.
yeah, I will see this. But we did research DSPy, and actually it's like a library full of different approaches, and they use all of the stuff I explained in the second part with different approaches. They like have implementations, their own implementations uh, of the most popular prompt optimization techniques, but we didn't use it because how do I say it? If you use DSPy, you can't use anything else. So you need to do your um, LLM calls using DSPy, and you need to use DSPy to do everything LLM related, right? And you can just put a text into some magic function and get better prompt as a result. You need to do all their stuff with signatures and propagating the different how did they call it, promptimizers.
So it's a bit more complicated, right?
Yeah.
There's more overhead when you want to use it.
You need to like be in the SPY ecosystem. And if you do, then you get great results and maybe
Hmm.
even better than our approach. But you
Hmm.
can just use it as
Hmm.
a like
Hmm.
separate prompt optimizing library. You need to use the whole stuff.
Because probably what I want to have is I have some prompt that is maybe not great, but kind of gives me a good baseline, and I want to make a few iterations on this baseline. I don't want to use a whole different library just for this, right?
Yeah,
So then evidently is better because I can just experiment with the prompt, come up with a newer version, put it in my agent, and then that's it, right?
yeah.
Until I
And
want to improve it again, right?
yeah, and to use DSPy, you'll need to
Yeah.
rewrite your agent to use DSPy basically. But then you'll get like free prompt optimizations, and you can just switch configs for different algorithms, and it will be really easy. But first, you need to like rewrite your code to use it.
Or start with it if you're starting a new project.
Yeah. Or if you're starting, then you just can go with it.
And another question I wanted to ask you is this one. Do you optimize and evaluate using the same model? Because maybe you also came across this recommendation is the evaluator and the agent should have different models, right? So agent, otherwise there could be bias. I don't know if you find any evidence that supports that statement that it should be different models, but I think in your case you use the same, right? It was GPT-4o.
I'm not sure because we actually when you use prompt optimizer, you specify only the model for the prompt optimizer itself. And as we saw, when you provide the executor function, this function can use anything inside. So with this example, you can see that we provide model for the LLM judge, not for
Yeah, I think
yeah,
here in
yeah.
this case it was
In,
for
in,
all.
in this case, we just used one. But
Uh,
if you add model argument for LLM function, then you can
yeah.
also separate those. And
I'm curious if it's actually really required. I don't know if you came across this problem. Maybe have you seen this recommendation that I definitely saw it, and the idea is that a model, let's say if you use GPT-4o mini, could be based towards its own output, and it can say, okay, like this is good because I produced it. While if you use like I don't know GPT-5 Nano to evaluate for O mini, then it might be more objective.
yeah, I think the general rule is you should optimize your prompts using smarter model, at
Uh-huh.
least not stupider model,
Mhm.
because like you'll get better results and you only need to do it once, so you can pay
Yeah,
more for the
yeah.
prompt optimization.
So you use plot 4.5 opus, right?
Yeah, basically any that is smarter or equally smart, at least. And I didn't see many cases when you actually need uh, different models. Maybe if you're using the cheap model for inference and for judge to be quick, to be cheap, then you can switch the optimizer to better one. But actually, in all our examples, um, I think we used GPT-4o mini, the mini version, which is uh,
Yeah.
stupider,
Yeah,
basically.
that's my to-go model in many cases, but when we want to optimize the prompt, it makes sense to use like a better model. But still, like for the agent, I still go for Omni because it's cheap, it's fast.
Yeah.
Sometimes it's really dumb, like it's super stupid. But
Yeah,
yeah, it is what it is.
but for our examples, it worked basically.
Mhm.
So it
Yeah.
can even optimize prompts. And if you
Mhm.
use even smarter model, the result should be even better.
Okay. Okay. Thank you, Mikhail, for this great presentation. Thanks everyone for attending it, for asking questions. I learned a lot. So for me, this is definitely new information. I enjoyed this talk and today example. It was really like it helped me to remember the presentation. So thanks a lot for doing this.
Yeah, thank you for hosting this event.
Okay, then I guess that's it. So enjoy the holidays and see you around.
Bye.